Welcome to the Science and Discovery program. The origin of the universe began with a spectacular Big Bang. The Big Bang triggered the exponential expansion of the universe. Since then, the universe has been continuously expanding to this day. But what exactly caused the Big Bang? How could something be born out of nothingness? We are about to embark on a journey to explore the beginning of time, attempting to uncover one of the most fascinating mysteries in the origin of the universe. What happened before the Big Bang? The universe is an immense structure, so vast that it is beyond imagination. But how did it all begin? The Big Bang theory can no longer be simply described as the origin of the universe. If the Big Bang was not truly the beginning, then what exactly was it? And what was the situation before it? Let us take a look at how science explains all of this. For more than half a century, we have obtained solid scientific evidence, proving that the universe as we know it began from an extremely hot and dense state. That is, the so-called Big Bang, or at least, we thought the universe's story began this way. Within a finite amount of time, the universe erupted from an extreme point. Today we know much more than in the past, but many unknowns still remain. Let us return to the origin of space-time itself to understand it all. About 13.8 billion years ago, our universe began from a volume of space smaller than a tennis ball. All matter and energy that we see today were initially concentrated within this tiny volume. Despite all this energy being packed into such a small space, the universe did not collapse into a black hole. Instead, it began to expand exponentially, and it has been expanding since the Stone Age. In the early 1920s, Vesto Slipher first observed the phenomenon of cosmic expansion. By 1929, Edwin Hubble, using some of the world's largest telescopes at the time, proposed the famous Hubble's Law. In the years that followed, scientists, based on Hubble's research, observed distant galaxies and supernova. The results were shocking. The universe was not only expanding, but the expansion rate was accelerating. No matter how beautiful the universe may be, it contains many observable phenomena that require explanation. One such phenomenon is the recessional velocity of distant galaxies, being proportional to their distance from us. This was first observed by Hubble himself. The distant universe appears less chaotic, more uniform overall, and in all directions of space. A faint, clearly visible cosmic microwave background radiation can be observed. This aligns perfectly with our observations. This framework is based on the Big Bang theory. It suggests that our universe began 13.8 billion years ago, originating from an extremely small, hot, dense, and violently explosive state. Over millions of years, as the universe gradually cooled, stars, galaxies, and planets formed in succession. Due to the impact of that Big Bang, the universe is still expanding to this day. This implies that the universe was hotter and denser in the past. When we attempt to trace the universe's history, we discover thrilling facts. The core idea of the Big Bang theory is this: if the current universe is filled with matter and radiation, and is expanding, then by tracing far enough back into the past, we find that the universe once existed in an extremely hot and dense state, to the point where the laws of physics may have broken down. Today, we can observe the universe extending in all directions for 46 billion light years, tracing back to a hot, dense, and rapidly expanding state. Intuitively, like many others, you might think this can be traced back to a single tiny, hot, dense state as the beginning. However, we should resist this temptation, because such understanding is completely incorrect. The Big Bang was not the beginning of everything. This point is explained by the theory of cosmic inflation, which is the best scientific theory about the state before the Big Bang. In 1979, a young physicist named Alan Guth laid the foundation for the concept of the multiverse. He and Henry Ty were curious about the formation of particles in the early universe. Alan discovered something special in his equations regarding the way particles formed in the early universe. In his mathematical calculations, he found evidence suggesting that, under extreme conditions of the early universe, gravity might behave as a repulsive force. We humans usually think of gravity as attractive, but the equations of the early universe revealed its other side. This repulsive gravity can disperse everything around it and drive the universe to expand outward, leading to large-scale expansion. This force was so powerful that it could expand a molecule to the size of a galaxy in less than 1/100,000th of a second. This realization led to the birth of the theory of cosmic inflation. The explosion theory does not simply push the Big Bang back to the start of time, but points to a limit we can trace back to a point of extreme temperature and density, but no further, according to the macro concept of cosmic inflation. Before this extremely hot, dense, and uniform state, the universe did not contain matter or radiation, but was filled with the inherent energy of the space structure itself. This energy caused the universe to expand at an exponential rate, making the universe flat, empty, and uniform until the scale of quantum fluctuations. Then the inflation stopped. The spatial energy within the universe converted into matter and radiation. This is the origin process of the hot Big Bang. This powerful inflation force eventually triggered the Big Bang. This repulsive gravity drove the universe outward. This cosmic inflation not only explains the mysteries that the Big Bang theory couldn't, but also made some additional predictions that were later confirmed. Regarding the phenomenon of cosmic explosion, although much remains unknown, the past 30 years of research have strongly proven that the explosive state did exist. It was a stage before the hot Big Bang, which is enough to explain what the Big Bang really is and what it is not. It is believed that in the distant past, our universe was hotter, denser, and more uniform than now. This doesn't mean the universe reached infinite heat and density, so that the existing laws of physics failed. As the universe expanded, cooled, and reorganized, we eliminated excess antimatter, generated protons, neutrons, and atoms, eventually forming stars and galaxies that make up the universe we know today. People no longer believe that space and time began from a single point, 13.8 billion years ago. It is a set of early conditions, but before that, there existed a set of unique conditions and cosmic inflation. The Big Bang may not be the absolute beginning of the universe, but it marks the beginning of the universe as we know it. It is not the origin, but it is our origin. It may not be the full story itself, but it is an important part of the greater cosmic story that connects us all. When exploring the state before cosmic inflation, all we have are theoretical speculations, because the universe of that time left almost no data or information. Perhaps the universe was eternal then, with a true beginning before it, or other possibilities we haven't imagined. According to our current observations, we cannot even conceive of all the possible scenarios under such extreme conditions. Our existing physical laws no longer apply. As for time, time itself may have been a new property of the universe that emerged after the Big Bang, or it may have always existed. However, according to our current understanding of physical laws, we cannot further explore the state before cosmic inflation. We will continue to search for clues about the nature and cause of cosmic inflation. Please keep an open mind to all possibilities, but also remember that pure speculation cannot replace the best results science currently offers. But one thing is certain: cosmic inflation occurred before the Big Bang. Any other claims have been outdated for over 30 years. Time, light, energy, and the mystery of the universe's birth are fascinating. For centuries, humans have gazed at the stars with awe, wonder, and curiosity, exploring the origin and nature of these magnificent celestial bodies. These questions have been themes of religion, Philosophy and scientific exploration since the dawn of human history. All great scientists throughout history have pondered these questions, offering various answers, sometimes even conflicting theories. Among them, one of the most well-known and widely accepted theories is none other than the Big Bang Theory. However, the reputation surrounding this theory is often accompanied by misunderstanding and misinterpretation of its true meaning and scope. Sometimes, even so-called experts in the field misunderstand it. For example, one of the most common misconceptions about the Big Bang Theory is that it describes the origin of the universe. In fact, the Big Bang Theory attempts to explain how the universe evolved from a particular initial event characterized by extremely high density and temperature. But it does not explain how the universe actually began. The essence and origin of the universe may even lie in what existed before this event, all beyond the known universe as we understand it, always filled with the unknown and mysterious. Another common misconception is that people often associate the Big Bang Theory with some kind of gigantic explosion. In reality, the original intent of the Big Bang Theory was to describe the expansion process of the universe from an extremely primitive state to the massive scale we estimate today through astronomy and astrophysical observations, though most explanations depict the universe's unbelievably rapid spatial expansion, a rate possibly faster than the speed of light. This process should not be seen as a conventional explosion. Beyond that, we must remember, no matter how grand this theory may be, it is still just a theory, perhaps close to perfection. Or perhaps it will be overturned. Look at this vast universe. Every faint dot of light represents a galaxy, each composed of hundreds of billions of stars. In the evolutionary process of the universe, gravity wove a massive web-like structure among these interstellar regions. These galaxies and galaxy clusters are connected by bridges of invisible gas and dark matter, stretching across hundreds of millions of light years. This web, formed collectively by galaxies, spans the entire universe, a colossal network expanding in all directions. Among these galaxies, some are home to star systems, one of which includes a bright star with 8 planets orbiting it. On one of these planets lives a species, humans who only in recent decades began truly understanding the world around them. In fact, it was not until the last century that we humans discovered everything around us was formed through the material cycles of stars. These immense stellar furnaces transform hydrogen into heavier elements. Without this process, nothing we see would exist. But where did the stars come from? How were they formed? These questions strike at the heart of our confusion about cosmic time, space, and the forces of nature. What we seek is not only the origin of things, but that moment of silence, the beginning of everything, which may even transcend all we know. It is a perplexing fact. The entire universe, all galaxies, and time and space themselves seem to have emerged from a singular manifestation. We must adhere to the scientific method, discuss only verifiable facts. Our goal is to uncover how the universe operates, and why it exists as it does, and the path to that goal relies on the only medium capable of revealing information about the cosmos. Light. Light from stars, nebulae, and galaxies holds abundant information. It is the key to understanding their true nature. The invention of telescopes and the subsequent rise of spectroscopy in the 19th century opened the door to modern astrophysics. Every point of light we see in the night sky, though it may constitute only a small portion of the universe's matter, is sufficient to decode the past, present, and future of the cosmos. From Earth, observing all the galaxies that compose the dense, thread-like cosmic structure, we see them tinged in pale red, as if we were viewing the world through tinted glasses. This detail alone reveals the universe's origin. Light carries a wealth of information waiting to be decoded. including the movement of celestial bodies in space. In fact, light waves shift, depending on whether the source is moving toward or away from us. A phenomenon known as the Doppler effect, where light appears redshifted or blue-shifted. Redshift indicates galaxies are receding from each other. Indeed, the entire universe is expanding in all directions. The rate of this expansion is clearly defined by the famous Hubble's law for cosmologists. This discovery was akin to winning the lottery. They yearned to know when this expansion began. Observations show that in earlier times, interstellar distances were shorter. Therefore, by tracing backward on the timeline, we can return to an era when all matter was extremely concentrated. Through this method, scientists deduced that about 13.8 billion years ago, the universe we know today was once condensed in a beginning point that defies physical logic, where temperature and density reached infinity. You might imagine this beginning as a massive black hole, but herein lies a common misconception about the universe. We should not assume that all matter in the universe was compressed into a single infinitely small point. This origin differs from a black hole's singularity. In a black hole, the singularity is formed by extreme matter density and immense gravitational forces. However, the Big Bang's beginning did not contain matter. It was composed of pure energy, even at this stage. Traditional gravity may not have formed as the four fundamental forces: electromagnetism, weak nuclear, strong nuclear, and gravity may have still been unified into an undifferentiated fundamental force. How long did this origin last? How was it formed? These remain major unsolved mysteries in science. What we do know is that this origin underwent violent changes, expanding rapidly with immense radiation energy. In an extremely short time, the universe expanded from atomic size to the size of an orange. This early inflationary phase rapidly unfolded the universe. As it continued to grow, it also began to cool. In just 100 seconds, the universe expanded to the size of our solar system, spanning billions of kilometers. During this process, tremendous energy cooled and transformed into matter, creating billions of subatomic particles, signifying the birth of the universe's first atomic nuclei. Roughly half of these were composed of ordinary matter, the kind that makes up us and our surroundings. The other half consisted of so-called antimatter, a form with properties opposite to ordinary matter. When matter and antimatter meet, they annihilate each other, releasing energy, a process known as annihilation. Thus, the universe's birth came with massive conversion and loss of matter and energy. Fortunately, a slight excess of matter over antimatter allowed a small amount of matter to survive. Even a 1 in 100,000 residue was enough to lay the foundation for the universe we know today. As time passed, this early universe of particles and plasma, hot and evenly distributed, began forming more complex structures. About 0.1 seconds after the Big Bang, the universe's temperature had dropped enough to about 1 trillion degrees, roughly 1 million times hotter than the sun's core, for quarks to group together, forming protons and neutrons. Around 1 second later, the cooling plasma began forming the nuclei of some of the lightest elements on the periodic table, like hydrogen and helium. The following 3 minutes were critical as the universe cooled to about 1 billion degrees. During this time, large amounts of hydrogen and helium nuclei formed, along with small amounts of lithium and deuterium. This process is known as primordial nucleosynthesis. In the first 10 minutes, the universe's diameter had already expanded to the scale of light years. It then continued to expand and cool for about 300,000 years. When the temperature dropped to a few thousand degrees, electrons previously moving chaotically slowed enough to be captured by atomic nuclei, forming the first electrically neutral atoms. This marked a turning point in cosmic history. From this moment on, the universe became transparent. Before electrons were captured, the universe was a dense plasma of charged particles, in which photons interacted constantly and could not travel far, rendering the universe opaque, like a thick fog. However, when negatively charged electrons began orbiting positively charged nuclei, forming neutral atoms, the electrical interference disappeared, the fog lifted, and light from the Big Bang could finally travel freely, making the universe gradually visible. Once photons were released, the radiation pressure maintaining the fluid state of matter could no longer resist gravity. Matter began to collapse, forming stars and galaxies, marking the beginning of the era of matter. These newly born stars and galaxies condensed from massive clouds of gas, forming nebulae, star clusters, satellites, and the first generation of stars. These first-generation stars were enormous nuclear furnaces, fusing hydrogen into helium, emitting light and energy. But their fuel was not infinite. Once fusion ceased, relentless gravity compressed these stars, driving them to extreme temperatures, densities, and pressures. In such extreme conditions, heavier elements like iron, gold, lead, and uranium formed. These heavy elements did not exist in the early universe. They were forged in the life cycles of stars, especially in their death throes through nuclear reactions. A star's life is a grand, dramatic journey. Massive blue giants, colossal beings in the cosmos, though short-lived, ended in supernova explosions, whose light rivaled entire galaxies. From these supernova remnants, boiling gases and dust swirled through space, forming new nebulae rich in over 100 chemical elements. In these nebulae, atomic nuclei may collapse further into neutron stars or black holes. Through the gravitational pull of these clouds, new generations of stars slowly formed, in various colors: white, golden, red, surrounded by giant gas planets and small rocky ones. About 5 billion years ago, from one such stellar explosion's remnant cloud, our sun was born. Where do we come from? Science offers a clue. We are descendants of the universe's beginning, born in the brilliance of stardust, forged in the searing cores of stars, nurtured in the violent aftermath of supernova. In less than 4 centuries of scientific advancement, we have answered these ancient and fundamental questions. We know the origin of the universe, its structure, its mechanisms, and its possible end. Though uncertainties remain, is there truly nothing new left to discover? Some say we are at the end of science, a notion born from its many successes. But this is not new. Just as many once thought the story was over after classical mechanics and thermodynamics seemed flawless, and after Maxwell's theory of electromagnetism, some famous scientists claimed physics was complete, advising talented students to pursue other fields. Yet, within years, relativity and quantum mechanics emerged, completely overturning classical physics. Nature always holds surprises beyond imagination.